Deep in the constellation Scutum lies Stephenson 2-18, a red supergiant so monumentally vast that if it replaced our Sun, its bloated crimson surface would devour Mercury, Venus, Earth, Mars, Jupiter, and stretch beyond Saturn's orbit, a cosmic giant that defies the very limits of what stellar physics allows to exist. There exists a star so incomprehensibly massive that even light, travelling at nearly 300,000 kilometers per second, would need almost 9 hours just to complete a single lap around its surface. If this behemoth replaced our Sun tomorrow, every planet you've ever heard of, Mercury, Venus, Earth, Mars, Jupiter, would vanish inside its blazing atmosphere, consumed without a trace. Even Saturn, nearly 10 times farther from the Sun than Earth, would find itself grazing the edge of this monster's photosphere. This is not science fiction. This is Stephenson 2-18, the largest star humanity has ever discovered. And if you're ready to explore something that challenges everything we thought possible about the universe, hit that like button and subscribe, because what we're about to uncover will change how you see the night sky forever. Let's begin. For most of human history, the true giants of the cosmos remained hidden from us, not because they didn't exist, but because we lacked the tools to see them. The naked eye can only perceive so much, and even the most powerful telescopes of the early 20th century would have missed Stephenson 2-18 entirely. This star sits roughly 20,000 light years from Earth, buried deep within layers of interstellar dust so thick that visible light simply cannot penetrate. When we look toward the constellation Scutum with optical telescopes, we see darkness where this titan burns. The discovery of extreme red supergiants like Stephenson 2-18 required a technological revolution in astronomy. The breakthrough came with infrared astronomy, which allowed scientists to peer through the cosmic dust that blinds conventional telescopes. Infrared light has longer wavelengths than visible light, enabling it to slip between dust particles that would otherwise scatter and absorb photons. In the late 20th century, infrared surveys of the Milky Way began revealing anomalies, bright infrared sources clustered together in regions where optical observations showed almost nothing. One such region appeared in Scutum, and in 1990, astronomer Charles Bruce Stephenson catalogued a dense grouping of infrared bright objects while surveying the galactic plane. At the time, technology couldn't resolve individual stars within this cluster with enough detail to understand what they truly were. The cluster was simply noted, labelled as Stephenson 2, and added to the growing catalogue of mysterious infrared sources scattered across our galaxy. Years passed, and infrared detector technology improved dramatically. By the early 2000s, astronomers could finally resolve individual stars within Stephenson 2, and what they discovered was extraordinary. This wasn't just another random cluster of stars. It was a stellar graveyard in the making, packed with an unusually high concentration of red supergiant stars in the final, fleeting stages of their lives. Red supergiants are rare enough on their own, massive stars that have exhausted the hydrogen in their cores and swollen to enormous sizes as they burn through heavier elements. Finding even a handful together is unusual. Finding more than 20 in one compact region, all at roughly the same evolutionary stage, is virtually unprecedented. This cluster represented a cosmic snapshot, a group of massive stars born together from the same molecular cloud, now dying together in a slow-motion ballet of stellar collapse. Among these dying giants, one star stood out. It was brighter in infrared than all the others, cooler in surface temperature, yet radiating an almost incomprehensible amount of energy. When astronomers began analysing its properties in detail, the numbers that emerged were shocking even to scientists accustomed to extremes. This star would eventually be designated Stephenson 2-18, though it's also known as Stephenson 2 DFK 1 in some catalogues. Initial estimates were treated with caution because measuring the physical size of stars at such distances is notoriously difficult and fraught with uncertainty. A bright star nearby can appear similar to a massive star far away, making distance measurements absolutely critical. The breakthrough came when multiple lines of evidence converged. Precise infrared photometry revealed the star's temperature and total energy output. Spectroscopic analysis confirmed it as a red supergiant of spectral type M6, one of the coolest and latest spectral types ever observed for such a massive star. Most importantly, improved distance measurements placed the entire Stephenson 2 cluster at approximately 20,000 light-years from Earth, roughly 6,000 parsecs. With distance, temperature, and luminosity finally constrained, the calculations became unavoidable. When astronomers applied the Stefan-Boltzmann law, which relates a star's total energy output to its surface temperature and size, the result was staggering. Stephenson 2-18 has an estimated radius of approximately 2,150 times that of the Sunday. To put this in perspective, that actually makes sense to human minds. This means the star has a radius of roughly 1.5 billion kilometers. If you could somehow place this monster at the center of our solar system, where the Sun currently resides, its surface would extend far beyond the orbit of Jupiter, which sits at about 778 million kilometers from the Sun, and would reach nearly to Saturn's orbit, which averages about 1.4 billion kilometers away. The star's volume is even more mind-bending. Volume scales with the cube of radius, so a star 2,150 times larger than the Sun has a volume approximately 10 billion times greater. You could fit 10 billion stars the size of our Sun inside Stephenson 2-18 and still have room to spare. Yet despite this enormous volume, the star is not extraordinarily massive by cosmic standards. Its mass is estimated at somewhere between 16 and 40 times the mass of the Sun, though uncertainty in distance and other parameters makes precise mass determination difficult. This reveals something profound about red supergiants like Stephenson 2-18. They are not dense, solid objects. They are better understood as vast, tenuous atmospheres held together by gravity so weak at the surface that material constantly escapes into space. The average density of Stephenson 2-18 across its entire volume is far lower than Earth's atmosphere at sea level, millions of times less dense. In fact, most of the star's outer envelope has a density comparable to what we consider a hard vacuum in laboratories on Earth. If you could somehow survive the intense heat and radiation, you could theoretically float through large portions of the star's outer layers without feeling any significant gravitational pull downward. The structure of Stephenson 2-18 is hierarchical and extreme. At its center lies a compact core where nuclear fusion still occurs, though no longer burning hydrogen as it did in the star's youth. This core occupies an almost negligible fraction of the star's total volume, smaller than the orbit of Mercury. Surrounding the core are shells where different elements fuse at different temperatures and pressures. Hydrogen burns in one shell, helium in another, and even heavier elements like carbon and oxygen undergo fusion deeper within. Each shell contributes energy, and all that energy must somehow make its way to the surface. As energy travels outward through the star, it reshapes the structure dramatically. In the inner regions, energy moves primarily through radiation, photons bouncing endlessly between particles. But farther out, the material becomes too opaque for radiative transport to work efficiently. At that point, convection takes over. Huge bubbles of hot gas rise toward the surface, cool, and sink back down, replaced by fresh, rising material. This is similar to boiling water, but the scale is incomprehensible. Individual convection cells within Stephenson 2-18 can span distances larger than the orbit of Jupiter. An entire planetary system could exist inside a single rising plume of gas within this star's atmosphere. This convective motion is actually what allows the star to maintain such an enormous size. Convection efficiently transports energy outward, preventing the outer layers from collapsing while keeping them cool enough that they don't blow away immediately. Cool surface temperatures mean less radiation pressure pushing material off the star, which allows the envelope to expand to truly extreme proportions. Each square meter of Stephenson 2-18 surface emits far less energy than a square meter of the Sun's surface, but there are billions upon billions more square meters. The result is a star that shines with a luminosity of approximately 440,000 suns, while glowing a deep, subdued red. The star's surface, if you can even call it that, is not smooth or static. It's turbulent, constantly changing, marked by enormous bright regions where hot material rises and darker zones where cooler gas sinks back down. The surface churns over timescales of months and years, reshaping itself continuously, and there is no sharp boundary. Unlike a planet, which has a relatively well-defined surface you could theoretically stand on, red supergiants like Stephenson 2-18 simply fade gradually from dense gas to tenuous plasma to near vacuum. Astronomers define the photosphere, the visible surface, as the layer where light can finally escape freely. But above that lies an extended atmosphere stretching millions of kilometers farther into space. The star's extraordinary size comes with extraordinary instability. Stephenson 2-18 is actively shedding mass through powerful stellar winds. Every year, it loses material equivalent to a significant fraction of Earth's mass, blown away by radiation pressure and pulsations that send shockwaves rippling through the atmosphere. This mass loss is one of the highest known for any star in the Milky Way. Dust forms in the cooling outer layers, absorbs starlight, and is pushed outward, dragging gas along with it. Over time, this process will erode the star's envelope, slowly dismantling the very structure that makes it so large. How did such a monster even come to exist? Stars like Stephenson 2-18 are not born as giants. They begin their lives as massive, hot, blue stars, burning hydrogen at ferocious rates. The key to understanding this star's current state lies in its birth mass. Stephenson 2-18 likely formed with an initial mass somewhere between 25 and 40 times that of the Sun, though the exact value remains uncertain. That initial mass determined everything that followed. Massive stars live fast and die young, while our Sun will burn quietly for roughly 10 billion years. A star with tens of solar masses exhausts its fuel in just a few million years. The reason is simple physics. Greater mass means stronger gravitational compression, which drives core temperatures to extremes. At those temperatures, nuclear fusion reactions accelerate dramatically. The star burns through its hydrogen fuel at a rate thousands of times faster than the Sun, producing correspondingly more energy. During its early life, Stephenson 2-18 was nothing like the bloated red giant we observe today. It was smaller, perhaps only a few dozen times the Sun's radius, but intensely hot, glowing blue-white and flooding its surroundings with ultraviolet radiation. For millions of years, it maintained a delicate balance. Gravity pulled inward, nuclear fusion pushed outward, and as long as hydrogen burned steadily in the core, equilibrium held. But hydrogen fuel is finite. As fusion converted hydrogen into helium, the core gradually filled with helium ash. Helium does not fuse as easily as hydrogen. It requires higher temperatures and pressures. Once the core ran out of hydrogen, fusion stopped there. Without fusion to counter gravity, the core contracted under its own weight. As it contracted, it heated up, and eventually temperatures rose high enough to ignite hydrogen in a shell surrounding the helium core. This was the critical turning point. Shell burning releases more energy than core burning had, and all that extra energy had to go somewhere. The only option was outward. The star's outer layers responded by expanding, ballooning outward over thousands of years. As they expanded, they cooled, and the star's colour shifted from blue to red. Stephenson 2-18 had become a red supergiant. This expansion phase is not unique to Stephenson 2-18. All massive stars go through it, but only stars in a narrow mass range expand to such extreme sizes. Stars that are too massive lose their outer layers too quickly through intense stellar winds, preventing them from ever becoming true red supergiants. They end their lives as compact, blazingly hot Wolf-Rayet stars instead. Stars that are too light never generate enough energy to inflate themselves this far. Stephenson 2-18 occupies a sweet spot where mass, internal energy production, and mass loss rates align perfectly, allowing it to swell to the largest size theoretically possible for a star. As the star continues evolving, fusion progresses deeper into the core. Helium begins burning, producing carbon and oxygen. Eventually, those elements will ignite as well, creating even heavier elements in a cascade of fusion reactions. Each stage produces less usable energy and lasts a shorter time. The star is racing toward a fundamental limit. Iron sits at the end of the nuclear road. Fusing iron doesn't release energy, it consumes it. When iron begins forming in the core, the star's nuclear furnace will shut down. At that moment, everything changes. Without fusion to provide outward pressure, the core collapses catastrophically in less than a second. Matter compresses to densities found nowhere else in nature except inside neutron stars. Protons and electrons are crushed together, forming neutrons and releasing a flood of neutrinos that carry away more energy than the star has emitted as light over its entire lifetime. The collapsing core eventually reaches nuclear density and suddenly stiffens, halting its inward motion. It rebounds, sending a shockwave racing outward through the star's envelope. This is the beginning of a core collapse supernova. For Stephenson 2-18, with its vast but tenuous envelope, the shockwave will encounter relatively little resistance. It will tear through billions of kilometers of gas in a matter of hours. When it reaches the surface, the star will briefly become one of the brightest objects in the Milky Way, possibly visible even from Earth, despite the heavy dust obscuring the region. The blast will heat surrounding dust clouds, causing them to glow intensely in infrared. For days or weeks, this single dying star may outshine billions of others combined. What remains after the explosion depends on how much mass is left behind. If the core's mass falls below a critical threshold, it will stabilize as a neutron star, an object the size of a city but containing more mass than the Sun, spinning rapidly and beaming radiation across space. If too much mass remains, gravity will overwhelm even the pressure from densely packed neutrons, and the core will collapse further into a black hole. Stephenson 2-18 sits near this boundary. Its extreme mass loss over time may reduce the final core mass enough to produce a neutron star, or the core may still be too massive, forming a black hole instead. Astronomers cannot yet predict which outcome will occur with certainty, but the supernova itself is inevitable. The outer layers of the star will be flung into space at thousands of kilometers per second, enriched with heavy elements forged in the core and during the explosion itself. Carbon, oxygen, silicon, iron, and dozens of other elements essential for planets and life will scatter across the surrounding region. The largest star we know will become raw material for future generations of stars and worlds. There is one final twist to this story that adds a haunting dimension to Stephenson 2-18's existence. Light does not travel instantaneously. It moves at a finite speed, roughly 300,000 kilometers per second, which is fast on human scales but slow on cosmic ones. The light we see from Stephenson 2-18 today left its surface 20,000 years ago, long before human civilization as we know it existed. The star we observe is not the star as it exists right now. We are looking into the past, seeing Stephenson 2-18 as it was during the last ice age on Earth. It is entirely possible that the core has already collapsed. The supernova may have already occurred. The shockwave could be racing outward at this very moment, and the photons carrying news of that cataclysm may already be speeding toward us through interstellar space. Or the star may persist for another 100,000 years, slowly bleeding mass into space, glowing red in the darkness. We simply cannot know. The present state of Stephenson 2-18 is hidden from us by the finite speed of light, separated by 2 millennia of cosmic time. The existence of Stephenson 2-18 forces us to confront fundamental questions about limits in nature. In a universe governed by physical laws, nothing grows without bound. Mountains can only rise so high before their own weight crushes them. Oceans can only be so deep before pressure transforms matter into exotic states. Stars, too, face limits. They can grow large, but only to a point. Stephenson 2-18 appears to sit right at that edge. Stellar evolution models suggest that as a red supergiant expands, its surface gravity weakens proportionally. At a certain size, the gravitational pull at the surface becomes so feeble that stellar winds and pulsations can strip away material faster than internal energy can inflate the envelope. The star reaches a maximum size where expansion and erosion balance. Push beyond that, and the star simply tears itself apart. Stephenson 2-18 sits precisely at this precarious balance. Its outer atmosphere is so weakly bound that it sheds enormous amounts of mass continuously. The structure exists not as something stable, but as a temporary equilibrium between opposing forces. And this explains why the largest stars are not the most massive ones. Stars born with significantly more mass than Stephenson 2-18 never become red supergiants at all. Their intense radiation strips away their hydrogen-rich envelopes early in their evolution, leaving behind compact, blazing hot Wolf-Rayet stars that are powerful but small. The largest stars arise only in a narrow window of initial mass, massive enough to generate tremendous energy output, but not so massive that they lose their envelopes before they can expand. The title of largest known star has changed hands several times over the past few decades. For years, UY Scuti in the constellation Scutum held the record, with an estimated radius of 1,708 solar radii. But improved measurements of stellar parallax from the Gaia spacecraft revealed that UY Scuti was closer than originally thought, which dramatically reduced estimates of its size. The current accepted radius for UY Scuti is only about 755 solar radii, still enormous, but nowhere near record-breaking. Other contenders have risen and fallen. VY Canis Majoris, with an estimated radius around 1,420 solar radii, remains among the largest known. WOG 64, a red supergiant in the Large Magellanic Cloud, was once thought to have a radius exceeding 2,000 solar radii, but recent observations suggest a much smaller size, possibly as low as 800 solar radii, especially if it has evolved into a yellow hypergiant phase, as some astronomers now suspect. Mycephae, with estimates ranging from 1,134 to 2,061 solar radii, comes close to Stephenson 2-18 but falls short. WY Velorum, with roughly 2,028 solar radii, is another near rival. Yet despite these competitors and the inherent uncertainties in measuring such extreme objects, Stephenson 2-18 consistently emerges at the top. Even the most conservative estimates place its radius above 2,000 solar radii, and many analyses suggest 2,150 solar radii, or even higher. The margin of error is large, perhaps several hundred solar radii, but every credible measurement keeps this star larger than all known rivals. Could there be larger stars waiting to be discovered? Almost certainly. The Milky Way contains hundreds of billions of stars, and we have measured the precise sizes of only a tiny fraction of them. Many regions of the galaxy remain heavily obscured by dust, even to infrared observations. Future telescopes with greater sensitivity and resolution will undoubtedly probe deeper into these hidden regions, potentially revealing even more extreme giants. But there are reasons to believe that Stephenson 2-18 is genuinely close to the theoretical maximum size a star can achieve. Stellar physics imposes hard limits. As stars grow, surface gravity weakens, mass loss accelerates, and structural stability becomes increasingly fragile. Beyond a certain point, a star simply cannot hold itself together. Stephenson 2-18 appears to be operating right at this boundary, an example of nature pushing stellar structure to the absolute brink of what physics allows. What makes Stephenson 2-18 truly significant extends beyond records and rankings. This star serves as a living laboratory for testing our understanding of stellar evolution. Every aspect of its properties, its mass, luminosity, temperature, radius, mass loss, rate, chemical composition, must be explained by theoretical models. If those models cannot account for something as extreme as Stephenson 2-18, then they are incomplete and new physics may be required. The star also challenges us to reconsider scale in the universe. We live on a planet orbiting a rather ordinary star. Our sun seems enormous because we experience it from so close. Yet entire planetary systems could fit comfortably inside the convection cells churning within Stephenson 2-18's atmosphere. The scale leap from human experience to cosmic reality is so vast that it defies intuitive understanding. We can write the numbers, calculate the volumes, draw the comparisons, but truly grasping what it means for a star to be 2,150 times larger than the Sun requires a fundamental shift in perspective. There is also a deeper connection between stars like Stephenson 2-18 and our own existence. The atoms that make up your body, the ground you walk on, the air you breathe, none of these existed in the early universe. In the moments after the Big Bang, only hydrogen, helium, and traces of lithium formed. Everything else, every heavier element from carbon to iron to gold, was forged inside stars. Small stars like the Sun produce carbon and oxygen, but cannot create much beyond that. It takes massive stars like Stephenson 2-18, to synthesize the full periodic table. When these giants explode as supernovae, they scatter their chemically enriched material across space. That material mixes with hydrogen and helium in interstellar clouds and eventually collapses to form new stars, planets, and, on at least one planet we know of, life. The iron in your blood, the calcium in your bones, the oxygen you depend on to live, all were created in stars like Stephenson 2-18 and distributed across the galaxy through violent deaths. In a very real and literal sense, we are made of stardust, and stars like Stephenson 2-18 are the forges that created the raw materials of our existence. One day, possibly within the next few 100,000 years, Stephenson 2-18 will vanish in a supernova explosion. From Earth, 20,000 light years away, the event might briefly be visible even through the heavy dust, glowing intensely in infrared wavelengths. Astronomers will study the remnant, reconstructing the star's final moments and learning how such extreme objects die. The explosion will enrich nearby molecular clouds with heavy elements, potentially triggering the formation of new stars. The cycle will continue. Stephenson 2-18's death will seed the birth of future stellar generations, carrying forward the cosmic process of recycling matter through creation and destruction. The largest known star exists not as a monument to permanence, but as a testament to impermanence. It burns bright and red against the darkness, a fleeting arrangement of matter held together by forces operating at the absolute limits of possibility. It challenges our understanding, expands our perspective, and reminds us that the universe is far stranger, larger, and more wondrous than everyday experience suggests. Somewhere in the constellation Scutum, hidden behind veils of interstellar dust, Stephenson 2-18 continues its slow march toward oblivion. We observe its past, waiting unknowingly for news of its future to arrive. And in discovering this cosmic behemoth, in measuring its impossible size and understanding its inevitable fate, we learn something profound, not just about stars, but about the universe itself and our place within it. If you found this journey through the cosmos mind-blowing, don't forget to leave a like and subscribe. Understanding the largest star ever discovered is just the beginning of exploring the incredible extremes hidden in our universe.